Hi everyone, my name is Stan. As Kat has said, I'm customer solutions team lead at GridGaink, and today I want to talk to you about networking in Apache Ignite and GridGaink clusters. So obviously, networking is a crucial thing, crucial layer for a distributed system. But when you think about it, what exactly does a networking layer and networking components do in a distributed cluster? So first of all, that one's pretty easy. All of our systems are designed to transfer and process and store data. So transferring data over the network is obviously the main networking function. But what's there other than data transferring? So when you say data, you normally imagine something that's business valuable, business critical, something that we actually process, something like banking transactions. And while this is the main part that is flowing around in our systems, there are actually some other messages, events, some controlling signals which also need to be delivered, but in a somewhat different way. So delivering cluster-wide events and controlling messages is another important function of networking, which is a bit different from data transfer, which we will see further. Next, other than transferring stuff, what does network do for us? So imagine you don't have your distributed cluster yet, so you need to create it. And to do that, you need to connect a bunch of machines to create a single distributed system. So finding and connecting to other nodes is also something that a network component needs to be ready to do. And finally, when we have our working cluster, we have all nodes connected together, data is flowing. Unfortunately, in the real world, something eventually goes wrong. And for that case, we also need some failure detection. And failure detection in a distributed cluster is also normally a function of a networking component. So these are the four functions which we are going to talk about, which compose what networking is for a distributed system. And as a reference, we will be using Apache Ignite. And as all of you probably know already, Apache Ignite is an in-memory computing platform and in-memory database, which has all of these different APIs, which are presented on this slide. And GridGaink is something that is running on top of Apache Ignite core and provides a lot of these additional features, especially valuable to those enterprise users, such as features for security and high availability of the systems. So without further ado, let's look at the first of our networking functions, which is data transfer over the network. So what can we say about transferring data in a distributed cluster? So obviously, this is what defines the performance of our system. The system is only as performant as its network and its networking protocols. Almost all of the data in our distributed cluster is going to be actual business data, the data that we actually process. As opposed to the data which is, this other controlling messages and events which are internal to the work of the distributed system. So given all that, the key for this function is speed. When we are talking about transferring data in a distributed cluster, we want to do this quickly. And by quickly, we mean both latency and throughput. So we need a component in our distributed cluster which can transfer the data, a lot of the data with minimal latency and with maximum throughput. So what Apache Ignite can do for us here? How Apache Ignite implements this? So in Apache Ignite, there is a component that's called communication. And this communication component is what implements high-speed data transferring in the cluster. Almost all operations in Apache Ignite use communication. Anything that you can imagine calling from public API, say key value data access, SQL data access, distributed computing jobs, all of that will underneath use communication and its as its networking layer, as its data transfer layer. Internally, communication is based on Java Neo, and Java Neo, for those of you who don't know, it is a part of Java Standard Edition libraries. It is a framework for building fast, multi-threaded, asynchronous, and blocking I/O, in particular network I/O, and it is used in Apache Ignite to implement this optimized, multi-threaded I/O layer. And to minimize the latency, protocol communication subsystem is using peer-to-peer connections. So every node is connected to every other node in terms of communication component. And by doing that, we can achieve minimal latency. We can transfer data from one node to another with just a single hop. And on the other hand, we need to remember that opening connections between each and every node can be costly. Each connection is a TCP connection, it is a TCP socket, and this is a surprisingly precious resource, and we need to budget those. And let's see next slides. Next slides on how Apache Ignite does that. So let's look at a typical topology in terms of communication subsystem. So let's look at this example cluster. So here we have 4 what we call Apache Ignite server nodes, which are the nodes in Apache Ignite cluster that store actual data, and 2 client nodes, which are the nodes which don't typically store data, but are used as a gateways in applications to access the cluster. Think about them as sort of drivers in JDBC for classic RDBMS databases. So let's look at a typical communication topology. So logically, in communication, all nodes are connected. So it forms a fully connected topology. All nodes are equal. All nodes are interconnected. Any node can open a connection to any other node. But at the same time, as we have said, just keeping all this connection always online can be sometimes costly. And because of that, communication doesn't keep open all of the connections. If an application is idle, it doesn't do anything in the cluster at the moment, as the application on the right on this slide, it won't have any connections open at this time. Typically, an active application would be connected to all server nodes at the same time because it will need to access different parts of the data, and different parts of the data may be partitioned on different nodes, and all servers are also typically interconnected. So this is basically how communication is implemented in Apache Ignite. Of course, it's a lot more complex underneath when there is actual Java Neo code, when there is actual protocols which help to implement guaranteed peer-to-peer delivery, when there is this logic that handles creating connections and stopping the idle connections. But logically, it all looks pretty easy, right? So data transfer is easy on the surface, but can be pretty complex when you dive underneath to look at how is it implemented to be performant. So this is our first function. So data transfer, nothing too fancy, nothing too complicated. So let's look at our next networking function, which is cluster events delivery. And what can we say about cluster events delivery? So we have already said that cluster events delivery and controlling messages delivery is something that delivers message across the cluster which are not actual data messages. And when we talk about this cluster-wide events, it's usually something that changes the state of the entire cluster. So say you have a new node that has just joined. So all other nodes need to learn about that new node which has joined our cluster. And for that, we need to generate this cluster-wide event, and we need to deliver it somehow to all of the nodes. And being able to do that is actually a base for a lot of other distributed protocols. If you look at a lot of distributed protocols, such as, say, consensus protocols, or I think almost anything that's running on a distributed clusters, they may depend on some way of your system to be able to deliver these cluster-wide events. So this component, this function, is actually a building stone for a lot of other more complex protocols and subsystems. This function does not need to have a high throughput. As we have said, almost all of the traffic in the distributed cluster is the actual data, which we, as we have already said, are going to deliver with our communication component. So here, it's not going to be a lot of data, not a lot of events. They are normally not that huge in size. Maybe they will just be a few kilobytes, not that big. So the speed is not the key here. But what is the key? And it turns out that a lot of these distributed protocols actually require you to have some global ordering of the events that you deliver. What does it mean? Let me illustrate. So say you have a cluster of two nodes, two more nodes, and two of your nodes try to simultaneously execute these operations. Create table with some different parameters, in this case, with different primary key on this table. So in this case, obviously, we can't create the same table with two different primary keys. So one of these operations, which happen simultaneously, must win and must succeed, and the other must lose and must fail. So how do we decide which of these events, which of these operations happens and succeeds, and which of them fails? So who was first, event A or event B? Let's try to answer that. In Apache Ignite, cluster-wide events delivery and some other functions are handled by a subsystem that is called discovery. Actually, all three other functions other than data transfer, which we have looked at the start, are handled by this discovery subsystem. Cluster-wide events delivery, nodes joining into a single cluster, and failure detection are all three handled by discovery. So these are the two network components that we have in Ignite. Communication, which handles fast, high-speed data transfer, and discovery, which handles the other three functions. So let's look more at how discovery works. Let's look at discovery's typical topology. And this is the same cluster which we looked at when we talked about communication. 4 server nodes and 2 client applications. But we will now see that in terms of discovery protocol and discovery subsystem, they are connected a lot differently than for communication protocol. So in terms of discovery, the nodes are connected in this complex topology. All servers are connected in a one-way ring. And one-way ring is what makes it a lot easier to implement global ordering of events. And we will see on the next slides how exactly does it work. But you can easily imagine that with a one-way ring, there is only one way to get from one node to another. And having just one road from one node to another node is important to be able to guarantee delivery order. Next, let's look at the clients. The clients are not in this ring. The clients are outside of the ring. Each client is connected to a server. And here we can see that clients are not equal. Clients and servers are not equal in terms of discovery. In communication, they are all the same. And in discovery, clients are separate. Why they are not in the ring is because clients are often less performant than servers. Say we have a client application which is slow, which can be more distant from other nodes than a server node. Say we have it in the ring, then the performance of that client node will impact our entire cluster. It will impact our ring performance. And we don't really want that. And to be able to provide better multi-tenancy, we separate these clients outside of the ring. So the ring is sort of the core of our discovery topology, and the clients are outside. The servers are also not all the same. One server is different from all the others, and that server is called coordinator. And coordinator is the main server in the topology which handles the event ordering. Unlike a lot of other systems, there is no designated coordinator. So any server node can become coordinator under different circumstances, but at any given time, the oldest node in the topology, meaning the node which has the earliest start time and cluster join time, is the node which will be the coordinator and which will help us to provide that event ordering. And we will see on the next slides how exactly does it work. And one last thing I want to mention here is that processing of discovery messages is single-threaded. So when we talked about communication, you remember that communication processing is multi-threaded because we want higher throughput and we want to focus on speed. But here we are focusing on ordering, and to provide ordering, you normally want single-threaded processing. So these are the basics of how discovery works. And now let's look at the ring message delivery protocol, at how exactly message is being transferred across the cluster. So say a node number 1 here wants to deliver a message to the entire cluster. We are not talking about what message exactly is it, just any message that changes the state of the cluster, we say. The message starts at the node number 1 as unverified. Unverified means that other nodes, when receiving it, will not process it. They will just push it further down the ring, but they will not actually react on it. So the node number 1 sends a message to node number 2. Node number 2 doesn't process it, sends it further. Node number 3 just sends it further. And here the message reaches the coordinator. The coordinator is the one who processes unverified messages. Coordinator makes the message verified. At this time, we say that the message is now ordered in relation to other messages. We say that a message is considered to have happened earlier than the other message if it has been verified on coordinator earlier. Or since we have only one way of delivering messages from one node to another, and since the processing is single-threaded, we know that if the message reaches coordinator earlier than another message, only in this case it will be considered to have happened earlier. So after coordinator has verified the message, it sends the message further down the ring, and now the nodes can actually process it. So now node number 1 sees the message, sees that it's verified, and the message says do stuff, and the node number 1 actually does the stuff. And the node number 1 sends that verified message further. Now it sends it to clients as well as to the servers, and now the client and the server will also process this message. The server number 2 sends the message further down the ring. Node number 3 processes it, sends it further, and when the message reaches the coordinator, this is when coordinator, seeing the verified message, it knows that it is actually on the second pass of the ring, and now it can just stop the message processing. And this is how we know that the message is processed on every node of the grid. So key points from what I have just described. So first, message makes 2 circles around the ring. First circle is for the message to be delivered to the coordinator, and the second circle is for the message to actually be processed. Second, event A is considered to be earlier than event B if it is verified on the coordinator before event B. And this is how we answer our earlier question. How we decide which event has happened earlier, event A or event B? Well, whoever reached coordinator first wins. So this is how event delivery in the cluster works, in Apache Ignite cluster works. And here we have seen that cluster event delivery is very different from data transferring, because in data transferring we need to focus on the speed, and because we focus on the speed, we need to do it in a single hope, in a fully connected topology, in a multi-threaded processing. Here, when we want ordered processing with global order across the entire cluster, we need this complex topology, and we need single-threaded processing and some more sophisticated delivery protocol. So next, let's discuss our third function of networking, which is getting the cluster together and connecting a new node to the cluster. So what does a node need to do to get connected? Well, that's simple, really. First, a node needs to find a cluster to connect to. And technically, it usually means finding IP addresses, finding IP addresses and TCP ports which the node will want to connect to. Next, the node needs to handshake with the new cluster, and handshake means that it needs to send a request to join, and it needs to hear a decision on whether it can join or not. And finally, it needs to exchange information with the cluster. It needs to notify other nodes in the cluster that it exists, it has connected, and needs to distribute information about itself. And it also needs to get some information about other nodes in the cluster in order to be able to communicate with them. So how Apache Ignite implements this is primarily with a little component called IP Finder. So IP Finder is a part of the discovery subsystem, and IP Finder is what tells our nodes, servers and clients how to find a cluster to connect to. IP Finder is actually an interface with a lot of different implementations, which returns a list of IP addresses a node can try to connect to. As I've said, it has many implementations. The most commonly used one is a list of statically hard-coded IP addresses, which works very well for most bare metal or any on-premises environments which are not private clouds. There is a sort of a lazy approach based on multicast, when you don't want to hard code all of your IP addresses. Say you have a huge cluster and you know that in your subnet there is only one cluster, then you can just use multicast to find all the nodes in the subnet which are currently running. There are a few implementations based on shared files or shared tables in databases, which is basically every node when starts, they write their IP addresses to that shared file, and when a new node starts, it reads that shared file, it sees addresses of all of the other nodes which have already started, and this is how it knows what it can connect to. And last but not least, there is discovery with Kubernetes and various cloud-specific tools, such as, say, AWS load balancers, which are pretty handy in a lot of these modern cloud environments, and and these implementations are getting more and more widely used. So now let's look at the algorithm of any cluster join actually. So say we have a cluster of these 4 server nodes, and a new client node starts, and it needs to connect to cluster somehow. What it will do first, it will ask its own IP finder running inside it on what it can try to connect to, and IP finder, any implementation, it just yields out some addresses. In this case, it gives a single address, which is actually an address of node number 1, and then the client tries to send a join request on this address. If a node is running on that address, which in our case it does, the node will process the join request and respond. Hopefully, it will say that the join is permitted. Sometimes it will not allow the client to join. For example, say you have some sort of security enabled on the cluster and you have some sort of authentication. In that case, the node number 1 may want to check the new client's credentials and may disallow the join. But in this case, say the join is accepted, and then the client establishes the discovery link with that server number 1 that it tried to connect to. And now we have our discovery link running, and now we can use discovery protocol, discovery subsystem to exchange information with the cluster. We can't use communication yet, but we already can use discovery. But what we actually want to do is we want to use our communication component to exchange actual data or transfer actual data to the cluster. To do that, we need to exchange information with the cluster over discovery. What our client will do is it will send its addresses, its IP addresses, and a lot of other attributes, a lot of our information about itself to the cluster over discovery. There will be a not joined event generated, which will be distributed across all of the nodes in the same fashion which we have already discussed. And that's how all of the nodes will know that there is a new client and they can communicate with it. And after that, the client, it will also get information about all of these nodes also over the discovery link. And after that, it will be able to establish communication connections and do some actual work. So the key points from this are: a new node starts by finding a running server node using its IP finder, and it establishes a discovery link with that server node. Then the discovery link is used to exchange information between the new node and the running cluster. And information, most crucially, includes the communication addresses and the info on how to connect to the cluster nodes with communication. And now after that, discovery, in this way, discovery bootstraps us to start doing some actual work with communications component. And this is how cluster join and connecting to cluster works in Apache Ignite. And this brings us to our last networking function, which is node failure detection. So what can we say about failure detection in Apache Ignite and virtually any distributed system? First of all, it defines high availability of our system. And failure detection defines high availability properties in the same way data transfer defines the performance. If we want high availability, we need to be able to understand that something bad has happened quickly, and we need to be able to react on that quickly as well. And this is why failure detection is so important. But we also need to understand what the failure actually means in a distributed system. So we could say that if we don't hear from a node for some time, then it has probably failed if we don't hear response, for example. But idle is not the same as failed, and we need to somehow distinguish that. If we don't hear from a node, if a node doesn't do anything, it could just be idle and ready to process requests, and we don't need to just kick it out of the cluster as failed. But the notion that network reachability and being able to send messages to a node and hear from the node back, this notion is actually correct, and a failure in a distributed system is normally attributed to network reachability. And finally, on the failure detection, we need to be detecting failures all the time. It can't be just ad hoc. We need to be proactive in our failure detection. Say, even if nothing is happening in your cluster, the cluster always needs to monitor the state of all nodes and kick out a node that is not healthy, so that when the actual work finally comes, it can start processing it right away and not bother with failure detection. So how failure detection is implemented in Apache Ignite? As we have said earlier, discovery is what handles failure detection in Apache Ignite. And in Apache Ignite, we say that a node has failed if we can't connect to it via discovery. Discovery links are always up and running. So if we can't send a discovery message to a node, then we say that that node has failed. If we don't hear from a node via discovery for some time, then we also say that that node has failed. And we have already said that we need to be detecting failures all the time. And for that, all nodes are constantly exchanging special messages, which are called heartbeats. And these messages are sent via discovery protocol, via the discovery ring. And this way, we can always say that all nodes are sending messages to each other. All nodes are hearing from other nodes. all the time. And if we can send a message to some node, or if we don't hear from a node, then something is not right. And let's look at a couple of examples of how exactly can it work. And the first example is actually pretty simple. So say node number 3 has failed. It could be just hanging, it could be in a garbage collection pause for a minute, it could be just completely failed, the process might have failed, network might have failed, anything could happen. But in this example, we say that the node number 2 can't send a message to node number 3. It either can't send a message or can't hear an acknowledgement on the message back. So something between nodes 2 and 3 is broken. In this case, it's easy actually. The node number 2 will realize that it can't talk to node number 3, but it knows about node number 0, and it will just bypass the node number 3, talk to 0 directly, tell it that, you know what, I can't reach 3, 3 is probably 3 has probably failed, and this is how node number 3 will be excluded from the cluster. In another example, say node 2 can actually send a message to node number 3 and can hear back. But node number 3 is still the one that failed. Say something is hanging inside of it. Say it has ran into some sort of a nasty deadlock, not allowing it to send discovery message further down the ring, but for some reason it still can read messages from node number 2. In this case, we say that we still need to somehow exclude node number 3 from the cluster. So in this case, we will invoke our second rule. We didn't hear from node number 3 or node 0 for some time. It means that probably node number 3 has failed. And node number 0 not hearing from node 3 for some time will initiate some failure detection routines, and the cluster will realize that it's the node number 3 which is not sending the messages further, and this is how the node number 3 will get excluded. And this was our last function actually, and these are the 4 networking functions: data transfer, cluster-wide events delivery, cluster join, and cluster node failure detection, which are implemented by the 2 components in Apache Ignite: discovery and communication. And at the end, let's look at the comparison of discovery and communication as the 2 cornerstone networking components in Apache Ignite one more time. So both are Ignite networking subsystems, but they are completely different in what they do and how they do it. Discovery handles everything that helps the cluster stay healthy and which allows the cluster to do all the things it does. So it handles cluster-wide event delivery, it handles node joins, it detects failures, and it does that with a single threaded processing in a complex topology when all nodes are different and all play different parts. In communication, it's all much simpler logically. All communication does is delivers data fast with a multi-threaded processing using Java Neo as an underlying low-level framework, and it does it so in a fully connected topology where all servers and clients are equal, And the complexity in communication actually lies only in how it is implemented to be as performant as it is. And these are all the main things I wanted to talk about today. So, Venkat, if you could tell me if we still have some time, I have a couple of additional topics here, but we can also just jump to the questions.
Yeah, I think you have another 5 minutes, Stan, if you want to continue.
Okay.
Yeah.
Okay. Thank you.
Audience, I mean, just
Then
there, if you have any questions for Stan, please put them in the questions panel, and we can line it up. Yep, go ahead, Stan.
Yep. Thank you. So while we're waiting for questions, a couple of advanced topics which showcase some of more difficult situations and some of more complex challenges which networking components have. And I just want to show you how these components may get even more sophisticated and even more complex to answer these challenges. So first, large clusters. So what are the downsides of the ring topology? If you have a large cluster, say 1,000 nodes, then you will have a node of 1,000, sorry, you will have a ring with 1,000 elements. And it means that the latency in that ring will be multiplied by the number of the nodes. And the latency will grow linearly. And this is not a good thing. I've said before that we are not focused on speed with discovery, but huge latencies which a 1,000 node cluster can give you with a ring topology is not a good thing. This will cause instabilities, this will cause a lot of very, very nasty issues. And there is actually a solution for that in Apache Ignite ecosystem. And there is an alternative discovery implementation for large clusters like that. And this implementation is based on Apache Zookeeper. So Apache Zookeeper is another distributed system also maintained by Apache Foundation. And what Apache Zookeeper does for Ignite, it serves as a central piece for delivering discovery events. In Zookeeper-based clusters, Zookeeper is the central part of the discovery topology. All nodes are connected directly to Zookeeper, which makes this a sort of a star topology with Zookeeper in its center. The benefit is that Zookeeper helps us to handle much larger clusters. I know of experiments with clusters of thousands and thousands of nodes connected to the same Zookeeper installations. And there are also some other bonuses. So Zookeeper can help you to, this Zookeeper-based implementation can also help you to protect from split brain, which we haven't discussed today, which is a nice added bonus if you have a large Zookeeper-based cluster. The downside here is, well, you need to also have a Zookeeper, and this is a whole another system which different rules which you need to maintain and which you need expertise on. So this is a trade-off here. So this is one of the advanced topics I wanted to show you. The other is one-way connectivity, or network address translation, or firewalls. So a pretty common example. Say we have a private network and a public network. Say, I'm saying on this slide internet, but normally this would be something like militarized zone and demilitarized zone, or just something in a network behind a net and public network. So say we have a client behind net and we have a cluster that to which that client can connect to. So the client can connect to the cluster, but the cluster can't connect back. It can't initiate the connection. So when we start working, the client just connects and it just works well. But at some point, you remember that all nodes are equal and any node can connect to any other node. At some point, a server node may try to establish connection back. It may try to initiate the connection itself. And practice shows that at some point it will happen. The connection will break, then server node will need to send a reply to the client. It will try to reestablish connection, and it just can't. It hits the net. It can't break the net. The connection can be established, and this can actually cause some very bad issues in the cluster. It can cause an entire cluster freeze. Because this situation is totally unexpected. And the solution to that is what's called communication via discovery, or indirect communication. So if a server needs to establish a connection to a client and it can't, then what it can do is it can use discovery subsystem, which is always on, and discovery links are always on, and it can use discovery to establish communication. So what it will do, it will send a communication request, but not directly, but across the ring, and the communication request is addressed to the client the node needs to connect. And when the communication request reaches the client will establish communication link itself. And now the communication link is up and running, and the server can utilize it to do the work it needed to do in the first place. And this is another example of how our always on, very stable, more complex and less performant, but more more guaranteed to be available discovery subsystem is helping us to establish our communication connections, which are what we use to do some actual work. And this is all that I wanted to talk about today. As a final note, if you haven't yet, please look at our community resources. Please join our Apache Ignite community. It is a great way to learn distributed systems and a lot more. You can contribute. You can just discuss issues and questions on community forums. We'll be glad to see you there. And if there are any questions, I'm ready to answer now.
Are there any visualization tools or dashboards that can show what's happening with these network components that connect to Ignite?
Unfortunately, not. There are some tracing capabilities in the product called GridGaink Control Center. This is a new product we have released just a few months ago, which is a monitoring tool for Apache Ignite and GridGaink clusters. It works well with both Apache Ignite and GridGaink, and it is available as a hosted version, available online without installation. You just connect your cluster remotely to the system running on in the cloud, or you can use an on-premise version. And it has a lot of these tracing capabilities, and one thing it can trace is discovery messages. So you can actually see how your discovery messages are being processed in the clusters, and this is really nice, especially when especially for those of you who might be interested in contributing to Ignite when you want to debug some code that you have written, but I guess it could be curious for other users as well.
Awesome. I just put a link for Control Center there as well. You can just Google Control Center. And maybe we are out of time, but maybe one last question. Do the usage of these network components, do they change significantly between, private and public cloud deployments?
No, I don't think so. Well, Apache Ignite and GridGaink, it works pretty similarly in private, in bare metal, and on private cloud and on public cloud. The main things which are different are, first thing I would mention is this, which I illustrated, one-way connectivity. One-way connectivity is a pretty common issue for cloud, especially for public cloud, and especially for Kubernetes. I have seen a lot of installations when there are applications running inside Kubernetes and server nodes running on bare metal. And in this case, you will get exactly this situation, and you need to use these one-way connectivity capabilities, which have actually been added just recently, I think just a few months ago. And this is what you need to work with Kubernetes in a lot of these environments. And another thing is IP Finder, as I have mentioned. So let me just scroll a bit back. So IP Finder it can be pretty different. So it has a lot of different implementations, exactly because different environments require different service discovery or different cluster discovery tools. So for example, if you have a bare metal installation, you have your 10 servers which always have these static IPs, then you want to just use a hard-coded list. But if you use Kubernetes, there is a Kubernetes IP finder for that. And if you use AWS, there are a couple of AWS IP finders which are useful in different situations. So I guess these are the main issues. Sorry, the main differences between different environments.
Awesome. Thanks, Dan. Thanks, everyone. Have a good day.
Bye-bye.